So I have posted a new active chemistry assignment. It should be 21, but I may have called it 20, but it's in chapter 6. So that one is due on Sunday because the material will be on your quiz on Monday. So you may want to make sure that you are looking at that. Your quiz on Monday is going to cover the last section of chapter 5 and then the stuff we've been talking about that's in the first 3 sections of chapter 6. I will get to talking about wavelengths and frequencies, but we won't do any calculations on your quiz. I may throw a bonus question in there, but you should know what the terms wavelength, frequency, and amplitude refer to. That's what you need to know from that first section. But otherwise, we've been talking about shapes of orbitals and stuff like that. Okay, any questions about any of that? Do you have it with you?
I hope so.
I hope so too. Okay, I have assigned a new active chemistry. This one should be 21. It is in chapter 6. And this is due on Sunday. So let's see, let's read 6.1 to 6.3 over the weekend, PTL 6A over the weekend, and active 21 in chapter 6. It's whatever one is in chapter 6. It's either 20 or 21, but we already had 20, so it should be 21, but I might have put it. Okay, so this one, all of this is due Sunday. And then we do have quiz 6 on Monday. Okay. We had just started talking about valence electrons and how we can count those valence electrons for each different column based on where things are on the periodic table. So I'm going to go back to that PowerPoint. And while I'm setting this up, see if you can figure out where my chocolates. See if you can figure out for, let's say, beryllium. For silicon and for sulfur, how many valence electrons they have. All right, so where are you going to look to figure out how many valence electrons? Okay, we have to look at the periodic table. And remember, everything in this first column has 1 valence electron. So how many does the second column have? 2. So beryllium is going to have 2. We skip over the transition metals. Okay, we don't consider d electrons truly to be valence because they don't bond in the same way as other things. That's inorganic chemistry, it gets weird. Let's look over here for silicon and sulfur. So how many valence electrons do you think would be over there? For silicon, 4, that is correct. Not silicon, but sulfur is 6. Yes. Okay. Let's see. This is the one. Excellent. Okay. So let me see if I can find, is it this one? Yeah, okay. Okay, so yeah, we said that, oops, this is the wrong one. There we go. These lines are representative of the energy levels around the atom. We number them from the bottom up. So the bottom one is energy level 1, 2, 3, 4, so on and so forth. And that we can put a certain number of electrons in each energy level. So the first energy level can only hold 2. And that is why there are only 2 elements in the first row. So we have hydrogen, which only has 1 valence electron, which are the, what kind of electrons? Where are they found? On the outside. And since there's only 1 ring, that's the outside. Helium is full. So the far right is full, the far left is 1 valence. Lithium then is going to have 1 valence electron, but when we get to beryllium, it does have 2, but it's not full. That line is a lot longer. How many electrons can fit into that row? 8. And so that's how we do those. Okay, now before sodium, so I've done 10 electrons here. 10 electrons would correspond to what element? With 10 protons. Neon, because remember our atomic number is the same thing as the number of protons. So neon also has a full shell, so it fits right underneath helium there. Okay, so that was our valence electrons. All right, so now we're going to take these energy levels and we're going to divide them up a little bit. Let's see, I changed the order on these. We're going to skip that for a moment, come back to it. Okay, so right now we have all of these electrons. I've kind of blown up the atom so I can just focus on these lines. We have all of these electrons that are here, but in reality, we don't really put all of those on one line. So we're going to use shorter lines. Now, the first energy level only gets 1 of these shorter lines. This shorter line is what we call an orbital. So the energy levels are made of orbitals. The first energy level, the whole energy level is 1 orbital. Okay, so it can hold 2 electrons. The second energy level is made of 4 orbitals. And so we have 4 lines. Each of those lines can hold 2 electrons. So 4 times 2 is 8. Okay, the third energy level is made of 9 orbitals, but they come in groups. So you'll notice that these 3 are a little bit separate from this one. These are right over the top of this one. And then there are these that are over to the side. And so the reason we get that 8 is because when we get to these elements, these 4 orbitals fill first, and then you start filling the other ones. So we have that set of 8, and then we have a set of 10. All right. So key points here. Oh, and then the other thing is, instead of dots, we are going to use electrons to arrows to represent electrons. We'll talk later, probably after Thanksgiving, about why we use the up and down arrows. But each orbital is going to have 2 arrows. So the line is the orbital, and the arrows are the electrons. Okay. So each orbital holds up to 2 electrons, and we use arrows to represent the electrons. All right, and so that is something that you kind of need to internalize, because a lot of your questions, both on your quiz and on your next test, are going to be about how are we representing electrons, how are we representing orbitals, okay? All right. So not all orbitals have the same shape. So your active chemistry is about the shapes of orbitals. So the one that was at the bottom is called an s orbital, and its shape is a sphere. So I've got these different styrofoam balls representing s orbitals. This can hold 2 electrons. This is a much larger s orbital. It also only holds 2 electrons. So the size does not change how many electrons can be held. Okay. All right, so the s orbital is spherical, and that's helpful. That's not where the name comes from, but that's helpful that it's s and spherical. Every energy level is going to have one s orbital. So there's an s orbital in energy level 1, there's an s orbital in energy level 2, and so on. In the first energy level, that's the only thing that's there. So the s orbital is the only thing that appears in all of the energy levels. All right, so the set of 3 that we saw are p orbitals. So this looks like a p orbital. And sometimes we say it's dumbbell shaped. Sometimes we say it's like an infinity sign. So here's my 3D representation. If you have it sideways, it kind of looks like an infinity sign. So these, if I change the direction, it looks a little bit different. It's still the same shape, but I can tell the difference between it being sideways and up and down. Whereas with a sphere, it looks the same no matter which way I turn it. Okay, and that's going to be significant because for everything except for the spheres, the way that the orbital is pointed is going to make a difference in how we label it. All right, so there's only one kind of s orbital. There are 3 kinds of p orbitals. So we can have one that is up and down. We can have one that is side to side, and then one that is also horizontal, but it's going kind of in and out. Okay, this one's hard to draw on paper. So sometimes you'll see me do it like overlapping circles as if you can kind of see this part and then just a little bit of that part. But they all look identical, even though you might draw the one coming in and out a little differently. And then the last one that we really care about is the d orbital. So the d orbital kind of has a 4-leaf clover shape to it. There are 5 different d orbitals. So there are 3 p orbitals. And they can go up and down, side to side, in and out. The d orbitals, and my styrofoam things are so old, they kind of fall apart when I try and do this. So I'm not going to do that today. But the d orbitals form planes. So it can form the plane that is like this, the plane that's like this, and the plane that's like this. And then it can also do diagonal planes. Okay. There are 4 that look like this, but the d orbitals is the one that has one shape that is different. So except this weird one, oops, need to do it on your slide, except this weird one. So there are 4 that are 4-leaf clover shape, and then one that looks like that. So it kind of looks like a p orbital that has a ring around it, a donut around it. I call it the ring of Saturn. Now we're going to start using colors to distinguish parts of the orbitals. And so when we do that, we'll see there's going to be a distinction between the p orbital and the shape in the middle there. S orbital. Okay, so a node is a no-no zone. That's where electrons are not allowed to be. So this means that an s orbital has 0 nodes. Now you're going to make some notes. You should have a spatula that looks like this. You'll have to share because there's only 1 or 2 per table. And you are going to cut your orbital in half. best you can. All right, so sometimes we draw a node in 2 dimensions on paper as a dotted line, but it's a 3-dimensional, like if this is a plane, I can stick my hand in between there, okay? Now, we are further going to illustrate the nodes by, we're gonna swap one half with another person, okay, with a different color. So if 2 people out of your table have yellow, I have a lot of yellow, swap with somebody that has a different color. All right.
Oh, I know.
So a p orbital has a node down the middle. So I'm gonna erase my s. It's gonna be a p orbital, and it has 1 node straight down the middle. Now, usually when we draw this, we don't draw it as half circles. So I want you to turn this into kind of a teardrop shape. All right, make sure you get a picture of your p orbital or somebody's p orbital. All right, so these get to the point where they almost touch, but they're like right at the nucleus of the atom. Can't have any electrons there.
So like the node is like.
It crosses through the nucleus, but it is also way above and way below.
Okay, got it.
Yeah. Okay, so the next part you don't need to write down. I just want to explain why we have different colors. This is because when we cross the node, we change sign. We don't change charge, we change sign. So what do I mean by that? Each orbital has an equation. So we might have an equation like y equals x plus 2, right? Now that's not the equation for these things. They have really complex equations. I'm trying to keep this simple. So if x is equal to 3, then y is going to be positive, right? And if x is equal to 10, y is positive. If x is equal to 100, y is positive, right? But if x is equal to -3, then y is negative, right?
Yeah.
So the equation that shows this orbital becomes positive on one side of the node and negative on the other side of the node. So anytime we have a node, the color changes, and we use colors because it's not the same thing as a charge. So in chemistry, we don't want to confuse it with a charge. But that just helps us to distinguish where a node is. So if I have 2 different colors, there's a node there. Okay, so that's the kind of the whole point of the different colors. So I had mentioned before that that d orbital kind of looks like the p orbital, but on the d orbital, it looks like this, and then the ring is a different color, something like that. So that's that funky looking d. You don't need to make that. I'm just trying to illustrate why it's a little bit different. Okay, so back to this guy. The p orbital had 1 node. The d orbital has 2. Okay, so where do you think I'm going to put that node? I have this one going vertical. Where's the other one? Horizontal. So you're going to take your spatula, try to get it divided in half. Now we're only going to need 2 colors, so you don't need to swap again. All right, so we said when we cross the node, we have to change colors. So I'm gonna swap two of these so that going over the line, the node, we have different colors. So there's a D orbital. How many nodes do I have in my D orbital? Two, so I'm gonna put a 2 here, 2 nodes. All right, you get a picture of that. Oh, on your homework assignment, it asks about nodes. There are actually 2 kinds. This is an angular node. Okay, we can also have what are called radial nodes, which I'm not going to get into, but you will see them in some of the pictures. You shouldn't need them for any of your assignment, but when you see them, you know, don't get spooked by them. The idea of an angular node is that it is this, I'm sorry, the idea of a radial node, this is part of the reason I don't do it, I mix up the words, is that it is the same shape, but there is a node kind of outlining the shape a different distance from the nucleus. So if I had a yellow one here and then an orange one here and a yellow one here, that would be showing the radial node as it changes from one color to the other. So we are going to ignore radial nodes. Basically, as I go up in energy levels, I add one more radial node. So my first d orbital has none. The next energy level up, it has 1, and so on and so forth. So you will see in the pictures that it will have like dark shading, light shading, dark shading, light shading. Those are the radial nodes. You don't need that information to answer the questions. Okay, so now, okay. So we use quantum numbers. Get that here? There we go. We use quantum numbers to describe our orbitals, okay? There are 4 kinds of quantum numbers that we are going to deal with. Today, I'm only going to talk about 2 of them. So the first one is called the principal quantum number, which I didn't write this down here. The principal quantum number, we use the letter N, and that's just describing the energy level. It's kind of like what level of the building are you on? Okay, first floor, second floor, third floor, and it can be any number, any natural number up to infinity. Okay, this also corresponds to the size. So when I say that this is n equals 1, like that doesn't correspond to like 1 nanometer. It just corresponds to the smallest size, okay? So I can tell that if I have an n equals 1 and an n equals 3, the larger one will be the n equal 3. That's how it corresponds to size. But what we're counting, the 1, 2, 3, 4, is the energy level, okay? Then we also have L, which is the angular momentum. This is called the azimuthal number, but you really only ever see that when this concept is introduced, so I'm not even going to bother writing it down. I do kind of like the name azimuthal. That's fun to say. But this is the angular momentum, and this basically tells us the shape, okay? So we call them by S, P, D, and F. That's how we've written those in our notes, but they also have numbers. And the numbers are going to help us with the third quantum number we'll get to on Monday. But the numbers are equal to the number of nodes. So an S has 0 nodes, a P has 1 node, a D has 2 nodes. So an F orbital will have 3 nodes. So those sets of orbitals, they come in sets. Each letter corresponds, or each shape corresponds to a certain number. So the S orbital, there's really only one shape. it's a sphere and there's only one direction, right? The p orbital, it comes in sets of 3. It comes in sets of 3 because it has 3 directions that it can use, but there's always going to be sets of 3. And so the d orbital comes in sets of 5. The f orbital, which is next, comes in sets of 7. The next orbital would be g. How many would be in each set there? 9. Yeah, it's a pattern. All of these quantum number things are based on patterns. Okay. So when I write about orbitals, I often describe them as the principal quantum number and the L, the angular momentum. So if I were talking about hydrogen, I would say hydrogen is using its 1s orbital. It's a very tiny orbital, the smallest possible orbital. Okay. When I talk about carbon, carbon is on the, using its valence electrons in the next energy level. So it has a slightly larger 2s orbital. It also has a 2p. Now this probably wouldn't be this big of a difference, but carbon has a 2p and a 2s orbital. Okay, so we can describe those differently. We're going to be looking at orbital diagrams. So this here is an orbital diagram. Okay, we number the energy levels from the bottom to the top. So this is energy level 1, and so we have a 1s. This is energy level 2, the second floor of a building. And so it has a 2s because every level has an s, but starting at energy level 2, it also has p. So this is the set that is called 2p. All 3 of those orbitals are called 2p orbitals. Okay. So I can represent an orbital by a line. This makes it really simple for when I'm trying to show where the electrons are moving, or I can draw the shape. So this also represents an orbital. So on your quiz, I might say, okay, does this represent an orbital? You're going to say yes. I might say, does this represent an orbital? You're going to say yes. And I'm going to say, does that represent an orbital? No. What does the arrow represent? An electron. Okay, so this visualization of different things is important for understanding what your chemistry professor might be trying to show you. Okay. All right. So when we have these different orbitals in sets, these are my d orbitals. I'm not going to deal with them right now. But when we have them in sets, the reason we have 1, 3, and 5 has to do with the next quantum number, and that next quantum number is going to tell us the direction. So sometimes you will see for the p orbitals the labels pz, which is up and down, py, and px, just telling you which direction it is pointed. Okay.
We see all 3 of those together, or just one of them?
So usually what they will say is they're talking about, say, a carbon atom. And they're saying, yeah, here's this carbon atom and it's got hydrogens, and then it has a px orbital that is overlapping with this carbon's px orbital. That's how they would talk about it. They all exist at the same time, but we usually only talk about one at a time. Okay, so that's all of those. Okay, so now what I want to do is I want to go to light. So this is the first part of the chapter. So now we have an idea of orbitals. Why do we care about the orbitals? Well, we can figure out the difference in energy here by the color of light that the atom shoots out when we set it on fire. Okay, so you're going to light some things on fire in lab after Thanksgiving. You're going to get different colors. Those colors are going to correspond to differences in energy level. Okay, so this is why we need to talk about light. Today, all we're going to talk about is light as a wave, just how we can measure light, and that kind of thing. And then on Monday, hopefully we will connect light back to the atoms. Light has had a bit of an identity crisis over the centuries. For a long time, people thought of light as being like little particles that were shooting out of flames and things like that. And then Einstein came along and said, you know, I can really demonstrate that this is a wave. And I don't think I'm going to get to how he demonstrated that yet. We're just going to talk about how we describe waves. There are two basic kinds of waves. This is a transverse wave, what we normally think of as a wave. And that is where the motion of the wave up and down is perpendicular to the direction the wave is going. So like a wave in the ocean is tall, but it is moving towards the shore. Okay, so that's a transverse wave. Sound waves are what we call longitudinal. So instead of something waving up and down, the air is being compressed or pulled apart. Okay, so it's a little bit different for that. We still use the same terminology. So the amplitude is how tall that wave is. So we have two waves drawn on here, and the arrows indicating the amplitude for the taller one is here, and the shorter one is here. And for an ocean wave, that corresponds to the intensity or the energy of that wave. So you might think about for light, that might be like how bright it is, or for sound, it might be how loud it is. Now, it turns out for light energy, it really corresponds to something else. So we're not going to talk too much about the amplitude, but you should know what the description is on a wave. Waves also have a wavelength. So this is the distance between two peaks or between two troughs. The troughs are the bottom parts, okay? Really, it's the distance between any one part of the atom and the same part of, any one part of the wave and the same part of the next wave. But if I'm trying to do this part here, I might accidentally think this is the wavelength. That's the mirror image. I want to go all the way to the next one. So that's why we usually use peaks and troughs. Okay, so wavelength is represented by the Greek letter lambda. That's a lowercase l. So you may be familiar with the uppercase lambda is kind of an upside down V, right? The lowercase lambda is kind of an upside down letter Y, okay? And that stands for wavelength. It is usually measured in meters. Then we have the frequency. And that's really kind of hard to draw in two dimension because it has to do with time. So if we are looking at a wave, we want to know how many times does it go up and down per second? Or if I'm thinking about this traveling sideways, then I might have like a police car with its radar gun right here. And in 1 second, how many of these peaks pass by? Okay, so if this represents 1 second of time, then that would be a frequency of 2. Okay, what are the units? So this one's a little bit weird. It is per second or cycles per second. We often say just per second, but since it's a little bit weird to have a unit of per something, there is also the unit hertz. So hertz means how many cycles per second there is. So you will see both of those on these slides. When we do the math, I tend to do it with the per seconds because we want to end up with a speed that is meters per second. We use the Greek letter N or nu for this. It looks like a V. It doesn't talk like a V or walk like a V. This is the Greek letter N, nu. And it is measured in cycles per second. And this is going to correspond to the energy. It's not exactly the same thing as the energy, but they kind of go hand in hand. Now we can measure the rate that a wave is going by how many cycles pass by in a second and how long that wave is. So meters times per second is going to give us meters per second, and that's our speed. For light, we use the letter C. This is because the speed of light in a vacuum is a constant. And it turns out that for air, it's pretty close to what it is in a vacuum. So we just kind of assume that it's the same number. And do I have that on here? No, I rearranged the equation. So nu is equal to C over lambda. And that would be how I would find the frequency. So if I know the speed of light, which is a constant, it's the same, and I know the wavelength, I can figure out the frequency. So what this means is that if I have the color of the light, which is what tells me the wavelength, I can figure out the frequency. If I have the frequency, I can figure out the color. And I don't think C is on here. No, it's not. I'm going to put it on here because we're going to use it. There we go. Okay, so C is equal to 2.998 times 10 to the 8th meter per second. I will always provide that for you, but we're going to use that number in a calculation in just a second. Okay. So if we compare different waves, we can see that if this all represents 1 second, if I have a longer wavelength, I'm going to have a smaller frequency. So I only have 3 waves, 4, just goes from 4 peaks there. And here I have a lot more than 4, right? So increased frequency versus decreased frequency. The other thing that we need to know is relative colors. So if you don't know the order of the colors of the rainbow, that's something you need to learn. Red has the longest wavelength, and that's what's shown up here. It's a lot longer or a lot shorter than that, but it's the longest wavelength. And then it goes from red to orange to yellow to green to blue. And then violet has the shortest wavelength. So that's something to know as well. All right. So sometimes I will give you a picture of a couple different waves and I'll say, which one has the longer wavelength? Which one has the highest frequency? So you have to look at those things. All right, so let's try a calculation here. If I have a red laser pointer, and the reason I pick laser pointers is they are monochromatic, which means they use one wavelength. So it has a wavelength of 650 nanometers. So a nanometer is 10 to the -9th meters. So we're going to have to start using scientific notation here. And we want to know the frequency. So we rearrange that formula to find frequency. Frequency is C over lambda. So C was 2.998 times 10 to the 8th meters per second. And we're going to divide it by lambda. So it's 650, but since it's nanometers, we have to put that in times 10 to the -9. Now that's not normally how we write scientific notation, but your calculator will be able to interpret that. So it's okay to plug it in that way. However, calculators, well, let me back up just a second. Remember from ideal gas law, if I had both pressure and volume on the bottom, I can't say divided by pressure times volume because my calculator isn't going to know that that's on the bottom of a fraction. So I either have to put all of this in parentheses and say divided by all of that, or I need to say divided by 650 divided by 10 to the -9. Okay. One way to get around that is to use the calculator's function of how it does scientific notation. So I'm going to show you on this one calculator how it works. You should check out your calculator. Each calculator is different. This is why I want you to have your own calculator. So if I look at this guy, these types of calculators, the small ones, have this EXP button. So I would write 650 EXP, and that means times 10 to the, and then I put 9 and then negative. I have to put the 9 in first and then the negative. If I put the negative before the 9, it's going to make a whole number negative. So notice what it looks like here. This looks like it's an exponent on the 650. Your calculator makes it look like that, but it's really 650 times 10 to the -9, okay? So plug in these numbers on your calculator, make sure that you can get that same result so that, oh, did I show you the result? Okay, I will put the result up, but make sure you can get that same result and know how you can plug it in. If you do this, do not put in times 10. You're just putting in the exponent. If you do that, you don't have to worry about dividing things. Divide this, because your calculator already knows. 0.6 times 10. Have a good weekend, and I will see you all